At the top we have a Systron-Donner model M107 precision DC voltage source. I got it a few years ago. It wasn't working and I did some repair and it worked except for the 1000 volt range, but that only lasted a few days before it screwed up again. So I want to look and see if the same fault that was there before has reappeared, or I know I did some dodgy soldering on one of the boards in there, maybe that's come bad. So we'll have a look. The service manual for this meter recommends calibrating using one of these. So Hewlett-Packard had a good opinion of it, obviously. And I haven't turned it on for a few years, so let's see what happens if I do. Transformer buzzes. Okay, now it's also got a GPIB interface on the back that can control the front panel. So the voltage setting can come from there, but we can do it from here. You see how we've got a digit blinking? We can put a number in there. Oops, clear. 1, 2, 3, 4, 5, 6. It's a bit dicky on some of the keys. 1, 2, 3. Oops. 1, 2, 3. Come on, 4. 4's not working today. 5, 6. And we get key bounce on the 6. And on the 1. No, 4's not working. Or a 7, or 8, or 9. Or you can pick a digit and just alter that one alone. The sequential light goes off and you can just put in a number. Naught works, 9's not working, 8's not working, 7's not working, 6 is working, naught works, 7, 8, 9 aren't, 4 isn't, 5, 6. Okay. So what you do is you set up your voltage that you want. So let's say clear and make it 1 volt, and pick the range and you have 1 volt. So that's 0.1 volt on 10 volt range. Now that becomes 1 volt. We can make 100 volt range, so it's 10 volts, or 1000 volt range. But when you select 1000, it goes into standby. You actually have to hit one of these outputs, plus or minus, before it actually puts the voltage out, and that doesn't work. And you can change the polarity plus or minus. And it's saying 9.9 volts, not 1 volt. We can go minus. You hear the relay click for the polarity, so that works. 10 volts. So 10 volts turns out 97. Go back to 10 volt range. Oh, it did double there, didn't it? So yeah, everything's a bit dicky. It's interesting how this thing works, so I'll describe that because it's worth going into a bit of detail on this thing. I did record a lot of footage when I repaired it last time, although I never made a video out of that. But I might include some of that footage. Some of it's pretty crappy, but we'll see. I'll show you how this thing works first. So here's a block diagram of the beast. This is simplified, of course, and it's more complex than this, and it's not exactly like this, but it's close enough. So there's two major sections. There's a digital section and an analog section, and they're connected via pulse transformers, which allow a signal to get across, but electrically isolated. So looking at the digital part first, we've got the front panel switches and the display, which we can enter those 6 digits into, and it gets into this register. And that register can also be loaded via GPIB from a remote source. Obviously, there's something wrong in this section, so that'll be one of the first things to look at. But once you've got your value in there, it's split off into the higher 3 digits, the most significant 3, and the least significant digits. So 2 groups. And because it's binary coded decimal, each digit is 4 bits, which can take on the values 0 through to 9. Values 10 through 15 aren't used. So we've got 4 bits per digit. Each group has 3 digits, so that's 12 bits. Goes into a 12-bit comparator, both of them. And they are compared with the output of this 3-digit counter. both comparators to the same counter. The counter is clocked at 1.15 megahertz, which is obtained from a 2.3 megahertz crystal. Dividing it by 2 through a flip-flop ensures that the duty cycle on this signal here is precisely 50-50. Even if there's some asymmetry in the crystal frequency, it's 50-50 after it's been divided. And so that counts up continuously from 0 and overflows when it would be showing 1000, and then resets to 0. And when it resets to 0, it sets these 2 flip-flops. The flip-flop remains set until the counter gets up to the value for those 3 digits, and then the equal signal comes along and resets the flip-flop. So if those digits are low, you get a short period of high before it's reset, and if they're 999, then you get a very long period before it resets, and you get something like this, a pulse width modulation output. There's the period there, which is about 1.1, a bit under 1 millisecond, 1,000th of that. If the count was 250, you'd only have like a quarter high before it goes low again. If the count was 500, it'd be half and half, and if it was 750, it'd be long. If the count was 0, then you get a very short spike upwards before it resets, and if it's 999, you get a very long high cycle, high half cycle, and then a very short notch before it at the end of the cycle. You've got this PWM signal, which corresponds to the value of the digits. Same again for the least significant. Now, those 2 outputs from the flip-flop, which are Q is high when that's high, and Q minus is high when it's not, so they're always opposite. It goes through an amplifier to drive it through the pulse transformer primary. So when it's set, the current's going one way, and when it resets, the current goes the other way. And that switching from set to reset and back again, these edges, when it goes up, when it goes down, when it goes up, when it goes down, provides a little pulse to the other side of the isolation barrier. So looking at the analog side now, you get something like this on the output of the transformer. It may be up the other way, I'm not sure. But you get a little kick when the pulse width modulation starts, and then when it drops down again, you get another kick in the opposite direction. So that period there corresponds to how long the signal is high, and then you'll have a dead period till the next cycle. So those 2 signals appear on this side of the pulse transformer, and there's another flip-flop which those signals trigger, and it reconstitutes basically that same pulse width modulation that we had up here. Basically it turns that, reconstitutes that on this flip-flop. Now this flip-flop drives 2 field effect transistors which act as gates to alternately connect the voltage reference, which comes from an LM299, 6.95 volts. It connects that to this point here, and in the other part of the cycle, when it's low, it connects it to ground. So this point here is going up and down between 0 volts and 6.9 volts with a duty cycle equal to the number that's been typed in to the front panel. So therefore the average value of that pulse, if you average it out, would be 6.95 times the value on the front panel divided by 1000. So if we had 500 in the top most significant digits, we'd have a voltage here which is, although it's a square wave, its average value would be 6.95 divided by 2. Likewise for the least significant digits, it does exactly the same thing. But here's the difference. The value coming out of the most significant 3 digits goes through a resistor to a summing junction, and from the least significant digits the resistor is 1,000 times higher. So that's how it makes the value of the least significant digits 1,000 times less than the most significant digits. So here we have a combined superimposed pair of square waves, but this one here is drastically reduced in amplitude to this one. So it's very lumpy, but when we put it through a filter, 6-stage filter, it comes out as a very steady DC voltage, equal to, or sorry, analogous to the number that we typed in on the front panel. It's anywhere between 0 volts and 6.95 volts. And that goes into the final part of the system, which is a fairly elaborate amplifier setup. There's there's a special analog devices block module thing there, and then it goes into a high voltage amplifier which is on a separate circuit board. The output is fed back so that it can keep the output steady. The feedback includes a bunch of resistors, and there's two relays which have 4 possible positions for 1 volt, 10 volt, 100 volt, 1000 volts. There's 4 ranges, and that controls how the feedback is set up to make the voltage appear here, make the voltage here what it should be for the correct input. Hope I explained that right. Yeah, anyway, this high voltage amplifier's got 140 volts power supply and a 1500 volt power supply when you're in the 1000 volt range. 2 other relays, one for polarity, which just swaps the outputs over to the output terminals, and the standby relay, which just cuts off the output and shorts terminals. I don't think I explained that too well, but yeah, a bunch of resistors controlled by relays change the gain of the amplifier so that the right voltage comes out for the range that you picked. And looking at it in schematics, this is the digital side. We won't look at it too closely. There's the crystal oscillator, divided by 2 flip-flops over here somewhere. There's the 3-digit BCD counter, and there's the comparators, the most significant and the least significant 3 digits. The voltage register is on another board. Its value goes into the comparators, gets compared with the counter, and the 2 signals, MSD and LSD, go through it's a bit complex. There's some sort of a ring counter thing going on there, but ultimately it appears that these 2 flip-flops, there's the drivers, the resistors, and they go to the pulse transformers. And then on the analog side, there's the 2 pulse transformers. The transformers toggle these 2 flip-flops. The outputs of the flip-flops control these 4 FETs, these 2 front FETs. That's the voltage reference up there. The 2 front FETs gate that voltage reference to their respective outputs. That's the most significant digit there, and when it goes through this one, it goes to here for the least significant digit, and then that's the summing junction where the 2 are combined. These 2 FETs out of phase of these 2 connected to ground, or actually slightly below ground. If you look there, you can see we've got 100 ohms plus 953 ohms. That's about a K versus about a meg, so that's where the 1000 to 1 difference comes from. So that's the summing junction. There we have our lumpy square wave, which has an average voltage proportional to what we've selected on the front panel. There's the filter network, so there's our nice steady DC voltage finally there, and then that goes into an analog device's special building block gizmo, and then into the high voltage amplifier board up here. The output of that then goes to all these relays. These 2 relays are for the polarity and standby that control how it gets to the output terminals, which are here. These 2 select the appropriate resistors in this feedback network back into the amplifier. So, clear as mud, isn't it? And looking at it, the pulse transformers are over here. These are the 1, 2, 3, 4. They're the this is on the analog side. The 1, 2, 3, 4. They're the transistors of the FETs. Of the flip-flops. And then these are the FETs. 1, 2, 3, 4. And there's the analog devices building block thing. That's the voltage reference. High voltage power supply board plugs into this. Plugs into that socket. And there's the 4 relays going back through this giant block of resistors, all potted away. It's a special component made by Systron-Donner. Very little information on it, but it seems to be nothing more than about 5 resistors. But it's a great big potted block. Bit of a picture of that. There we go. There's the pulse transformers. This is this aluminium wall here separates the analog section to the left from the digital section to the left from the analog section here, and you can see that they've embedded the pulse transformers in the wall. Yeah, it really represents the barrier between the 2. So they go in. There's the 4 transistors for the flip-flops. There's the 4 FETs. There's the voltage reference. There's that analog devices thing I was talking about. Now, those relays too also have to be controlled from the digital side, but they're on the analog side, and you can see there are opto-isolators down the bottom. They control the relays, so which don't have to switch anywhere near as quickly as the analog signal. So maybe they've had to use pulse transformers there for speed or for timing fidelity. Not sure. Other things like this do it with optocouplers, but they've used pulse transformers. That's the high voltage amplifier. Excuse the picture. You see these big heat sinks. Now, these heat sinks have 1,500 volts on them, and they project. It's sitting just here. They stick into this area here. So if you're trying to probe in here or make adjustments, there's no adjustments here, I don't think. No, they're all on the other side. But you might want to be probing in here, and you've got 1,500 volts sitting there. So yeah, not nice. Oh, there is an adjustment there, and there's two of them. These are also adjustments, these tall things with the wires hanging off, but the screws for them are on the bottom of the PCB. Oh, this is what I was talking about. There's the pulse width modulation signal going into the transformers, and this is what you see on the other side. A kick when it goes one way, and when it switches the other way, you get a kick in the opposite direction. Now, when it wasn't working before, this is the output of the flip-flops, these two flip-flops that are fed from the pulse transformers. This is what the output on one of them was. Instead of going low and staying low until the kick, it went high again. And likewise on the other side of the flip-flop, the other collector. That's looking at the collectors of these two transistors. And it turns out what was wrong was I replaced all those 4 transistors, didn't fix it, but 3 of these 4 FETs were dead. They were loading down the outputs on these flip-flops, and that's why they weren't flipping or flopping. So yeah, replacing those, fixed it. Couldn't get the 1,000 volt range to work, and I can't see why, because there's very little difference between 1,000 volts and any other range. It's just a slightly different resistors are switched in on the feedback. Don't know what's going on there, and never got that sorted. But so I'll be very interested to see if these FETs have failed again. But of course, first I probably have to fix that front panel. So let's have a look inside it now. I've been raving on long enough. So we're already at 17 minutes. I think I'll make this a teardown video, so it's not too long, and then if I have any success with repair, I'll make a separate video about that. So we'll just have a look inside it now. We've got some winter sun coming through. Hope it's not too distracting. So digital section, 3 boards there. That's the main board with the crystal oscillator, the flip-flops and the comparators and things. The other two are to do with the HPIB, and there's the display board that I'm going to have a closer look at. I'll try and take the front panel off and show you that. And yeah, something wrong there with the switches. And underneath this cover we have the analog section. So power supply here, 2000 volt 2 microfarad capacitor. All the other voltages are in there. There's the high voltage amplifier board, the relays, and I'll take these 2 covers off so we can see what's under them. There's the 2 pulse transformers coming in from the digital side, and there's also 4 optocouplers bridging this interface between digital and analog. Okay, screws are out. There's the big potted thing I was talking about. There seems to be only about 4 or 5 resistors inside that thing. It's some custom made block by Systron-Donner. Under this cover there's our voltage reference, the 4 FETs that do the switching, the 2 flip-flops, so those pairs of transistors over there. I'll use instead. Analog devices, 52K. Can't find any data on that thing. It's just some highfalutin amplifier. There's also an op amp there. There are adjustments. These things are all adjustments, so there's quite a few of them. I'll take the bottom off and show you that as well. And I'll take out the high voltage board. You know, the high voltage board is held down by a couple of screws which I've loosened now. And see, these heat sinks, 1500 volts, right next to where you might want to be probing things. And a complete lack of test points as well on this thing is damn annoying. I'll put a link in the description to the service manual for this thing, and I'll also show you the schematic for this board. Let's have a look at the bottom. You can see a few scratchings of mine to identify the power supplies because they didn't put any test points in. It's even worse under here. Here's the adjustments that all those controls up the top poke through to. So you don't have to take the cover off to do the adjustment. We'll take the cover off. Removing the cover. It's actually circuit board. It shields just the copper on one side of the circuit board, so that's good, so that because you've got a lot of nasty bolts under here, you don't want them touching this. There's my scratchings of components and voltages. They're the adjustment points, all these things, and they've got nuts to lock them down. Signals going into the high voltage amplifier. So now I'll take the front panel off. I might as well show the two boards for the GPIB interface. Just digital logic, nothing amazing. Pretty sparse, and there's also some logic on the digital motherboard. In fact, that may be the voltage register down there, which can be driven either from the front panel or from the interface board. I decided to make these wires too short to drop it down very far, but yeah, I've got to get that board out of the buttons to try and clean them up. And those screws don't come to the front, so looks like I have to undo them by the nuts. Yeah. Display board looks like it comes out pretty easily. It's got an edge connector there. And it's screwed down, but yeah, 2 screws and that should come out of this edge connector. Do I need to take it out? Maybe not. But I've got to get this board out to look at the switches. I've taken those 2 screws out of the display board, so it should come out now. Not the one with the displays on it. Alright. I'm going to have to drop this down. It's damn annoying that I didn't make those wires just a little bit longer, or put a connector so it could be unplugged and you could just drop this off. You know, they've got connectors everywhere else, why not for that? And having come this far, I might as well take this guy up as well. So there's the displays. Probably do a little bit of a clean. And now I can get at the button boards. And I've got the two button boards off. So hopefully there's just something dicky on that switch. It doesn't feel very good. And in my manhandling, one of the wires has come off the current limit pot. So what I think I'm going to do is note where these wires go and replace them with just slightly longer, maybe only an inch longer, so that this can lay flat in front without any stress on the wires. 6 wires have to be soldered. I see why they probably don't use connectors. It introduces thermal issues with those tiny little voltages, because this can go down to a microvolt. Or maybe I won't, maybe I'll just fix this. So first up, looking at the keyboard to repair it, you can see this key works, and if I try, say, the 4 key, buttons, I don't know if the button itself is broken or it's just so yeah, that's pretty much it for what's inside this contraption. I think we'll leave it at that for this video, and if I have any joy with repairing stuff, I'll make a second video. Hope you enjoyed. Please give it a like if you did, and I'll catch you later.